So in class on Monday, we had a problem like this where we had these two same points, 1, 4, and 3, 16, and you had to find the slope-intercept form of the equation of a line that goes to those 2 points. You had to find the slope and solve for the y-intercept. This is a different problem. It says find an exponential function f of x that also goes to these same 2 points. You will be able to find such a function as long as the 2 points are not on the same vertical line. If they're on the same vertical line, that would be trouble, right? Because then it would fail the vertical line test. No function would go through those 2 points. And you also want for an exponential function for them to be have the same sign, positive or negative, for the second coordinate. What kind of formula are we after? I typically write it like this: f of x equals a times b to the x. And I need to solve for a and b. If you use different letters, that's okay. And in fact, the textbook uses different letters in the reading. I will tell you in a few minutes what the textbook uses. It doesn't matter what letters you use. It's the idea that's important. Kind of like with the notation for Monday, it didn't matter what subscripts you use. It's the idea that's important. Is there a dependent variable? Well, sure. Whatever the output is, you could call that the dependent variable. X is your independent variable. Y is your dependent variable. I'm using just abbreviations here. Independent variable, dependent variable. X and Y are the standard things to use, but you don't have to use X and Y, and quite often in our textbook, they don't. In fact, quite often they'll use T for the independent variable, especially when it represents time. And for the dependent variable, yeah, they do use different things. And in fact, in this section, 1.2, they use P. You might think of that as representing a population. Q. You might think of that as representing a quantity. The variable you use is helpful sometimes for emphasizing the meaning for the application. F is the name of the function. That's the function name. Function name. What is a function? It's an abstract idea. It's a rule of assignment that for any given input gives you exactly one output. You've probably heard that before. Maybe you don't remember it. We give functions names. What is f? Is it a number? Is it just a letter? It's a letter that represents the function. It's the name for the function. Question? Yeah, we usually use f, but since, yeah, the word function starts with f. But be flexible, we'll use other letters too. You say f of x. Put that word of in there. That's very standard when you look at this. It's not multiplication. X is a variable. It does represent a number. F is not a number. It's not f times x. It's f of x. What does it mean to say the graph goes through these 2 points? This first point being on the graph means that when x is 1, y is 4. When you replace x with 1, when you substitute, y becomes 4. So this gives us an equation, y equals 4 when x equals 1. So 4 equals f of 1. I also could have written f of 1 equals 4. This thing here is the formula for the function. It's what defines the function. It defines the relationship, telling you how to find outputs for inputs. This is very relevant in, for example, computer science. In computer science courses, you're quite often defining functions. Much more complicated than this kind of function, actually. They can do some pretty wild things sometimes. Not just give you numerical outputs for numerical inputs. You replace x with 1. We don't know what the constants a and b are. That's what we're trying to solve for. This is showing that when I replace that x with 1, I get 4. So this equation must be true. Of course, b to the first power is b. I could write this as a times b. Of course, you should know that when you've got two different quantities represented by two different letters, if I write AB, it's understood that that means A times B. But if you want to be careful, you can also just put the dot in there for multiplication. The second point, 316, means that when x is 3, y is 16. 16 equals f of 3. When the input is 3, the independent variable is the input, the output, the dependent variable will be 16. The formula tells you how to find the output y when you know x. We know x is 3, we plug in x equals 3 and get this. I could write AB cubed. It's understood when you write AB cubed without a dot that it's a multiplication. A times B cubed. That's understood. You got to solve this system of equations, which is really a nonlinear system here, for the unknowns A and B. This was actually simple enough that maybe you guessed the answer. A is 2 and B is 2. Yes? Did you guess that? Maybe you didn't even bother writing these equations down. But what if it was more complicated? Could A and B still be solved for? It's actually a nonlinear system because we have a cube power there, a third power. So in general, nonlinear systems are hard to solve, but this one's not too bad. What you end up doing is you want to take the right-hand sides here. Well, you want to divide one equation by the other. It's a little strange. Sometimes we're used to adding equations or subtracting equations, but here we're going to divide one equation by the other. I'm going to take the second equation and divide by the first equation. So on the left-hand side, that's 16 divided by 4, and on the right-hand side, that's AB cubed over AB. The reason that's a good idea is that we get nice cancellation on this side. The A's completely cancel. And with the B's, you can subtract the exponents and get a B squared. 16 over 4 is nice. That's 4. So B squared is 4. So B must be what? Plus or minus 2? Well, in general, the solution set of this equation, B squared equals 4, is plus or minus 2 when actually both 2 and negative 2 are solutions. So it's a little weird saying or, but that's what we're used to. However, for this situation, if we're going to get an exponential function that works here, you really do want B to be positive for exponential functions. I mean, it's not that you can't put a negative number in for B, but those end up being kind of weird functions. So we want to avoid negative numbers for B. Let's just go ahead and say B is the square root of 4. And when I write the square root symbol, I implicitly mean the positive square root. If you wanted both square roots, you'd want to write the plus or minus symbol in front of these things. B is 2. Then you can go back to either one of these equations and solve for A. They should give you the same answer. If you use the first one, you'll get 4 equals A times 2. So A is also 2. If you use the second one, you would get 16 equals A times 2 cubed, A times 8. So once again, A is 2. You don't have to do both things. I'm just illustrating that you get the same answer either way. I'll put that one in parentheses. Again, you may have just guessed the answer and gotten it right. And that's good, but I could certainly make this problem harder by picking weirder examples for the coordinates. And then you'd have to do this kind of thing to solve for A and B. And I often do put that on exams, that kind of question, with harder numbers. So you do want to make sure you understand the process here. Can I clarify anything? So the answer is y equals f of x equals 2 times 2 to the x. Can I just write the answer as f of x equals 2 times 2 to the x? Yes, you can. Can I just write the answer as y equals 2 times 2 to the x? Yes, you can. Either way is okay. Can I do what I did, write both a y and an f of x? Yes, you can. Be flexible. It's okay. Any way you want to do it. Writing variables like a y emphasizes what the dependent variable is, and maybe it represents something like a height, a y coordinate. That would be nice to emphasize if it's an application. Using function notation is handy because it's nice to give functions names when you're working with them a lot. This function's f, this function's g. You're distinguishing between them. They have names. You may have had a teacher who described functions as being like machines, and yeah, I kind of think that's a fun way to describe functions. Are they literal machines? Well, no, of course not, but pretend, use your imagination. That's f, this box here with these tubes for input and output. And we know, for example, for this function, that when the input is 3, the output is 16. F of 3 equals 16. It's like you imagine 3 gets plopped into the function, and then, okay, yeah, you could imagine buttons on the box. But you could be old-fashioned and imagine a crank. Crank that function and out pops. Do you already make a popping sound? A 16. Plug in a different number like 5. What's f of 5? 2 times 2 to the 5th. Which is really 2 to the 6th. 64. F of 5 is 64. You plug in 5, turn the crank, you get 64. Can you plug in negative numbers in here? Yeah, you can. F of, for example, negative 5 can be found. It's 2 times 2 to the negative 5. You can add those exponents and get 2 to the negative 4. Most people reach for their calculators, but you don't have to. 2 to the negative 4, by definition of negative powers, is 1 over 2 to the positive 4. And 2 to the positive 4, do it in your head, is 16. This is 1/16. I can plug in any number for x into this function. The domain is all real numbers. Question? That's also correct. Yep. Thanks for bringing that point up. You could also add the exponents there. Usually A and B are different. So usually you don't want to add the exponents because A and B are different. So you really can't add the exponents. It's only because in this example, A and B are the same. They're both 2, that you could do what you did and write that as well. The domain is all real numbers. This fancy looking R represents the set of all real numbers on a number line. Any number you can think of, besides imaginary numbers, is on there somewhere. Sometimes people also use interval notation with infinity symbols like that. But remember, infinity for us is not a number. It's just a symbol that represents an idea, and this notation just represents that every number is in the set. No matter how big it is positively or how big it is negatively. What's the range of this? What are all the possible outputs of this function? Exactly, any number greater than 0. You could write that with interval notation as the open interval from 0 to infinity. Notice there's a parenthesis by that 0. 0 is not a possible output of this function. You can get really close to 0 if you make x a large negative number. The outputs get closer and closer to 0, but they never reach it. They can get arbitrarily large. This function grows as x gets bigger very rapidly. It's exponential growth. So I could use this notation. I could also use the set builder notation, curly braces, the set of all, should I call them X? Well, since it's outputs, I probably should call it Y just to avoid confusion. The set of all Y values such that Y is positive. The textbook, by the way, doesn't use the set builder notation with the curly braces. I like doing it though. It's a bit more official. You read this as the set of all Y is understood to be a number here, such that, or with the property that Y is positive. The line means such that, or with the property that. It's emphasizing it's a collection of numbers. What does the graph of this function look like? It still goes through those 2 points. 1, 4, and 3, 16. Goes through plenty of other points too. It's not a straight line. It's not a linear function. What's f of 0? What's the y-intercept? Plug in 0, you'll get 2. No matter which formula you plug it into. That's the y-intercept, 2. We saw f of -5 is 1/16. -5 is right there. It's going to be very close to the horizontal axis. The second coordinate is 1/16. 0.0625, I think. Getting close to 0. You plug in bigger and bigger numbers, it gets larger and larger. The graph ends up looking like this. Oops, I missed that point there. It's looking pretty straight over here, but it's actually not straight. But then it definitely curves pretty rapidly after this point. It's hard to draw perfectly. I mean, you might say it's impossible to draw perfectly. But try to do a reasonable job. Again, yeah, it looks like it's straight over here, but it's not. That's an illusion. That's me drawing it badly, in addition to just being hard to tell that it's not a line over here. It is actually still curving here. The curvature gets more over here. A generic graph that looks better might be like this. You can tell more easily that it's not a line over there. The domain is the set of all x values that can be plugged in. The range is the set of all possible outputs, which includes every possible positive number, but not 0 and not negative numbers. Okay, so again, this is exponential growth. It is an example of something called a one-to-one function. First of all, the graph is the graph of a function because it passes something called the vertical line test. I'm not going to write the vertical line test out in words, but I'll say it. And you should know this. Maybe you want to write it down by shorthand. The vertical line test says the graph will be a graph of a function if no vertical line goes to the graph more than once. Another way to say that is all vertical lines go through the graph at most once. So if I draw a graph that, for example, is a sideways parabola, that's not the graph of a function. It fails the vertical line test. There are plenty of vertical lines that go through it more than once. You can make graphs like that. And if you think of it in terms of y being determined by x, they're called relations. Excuse me. But they're not functions. Because for functions, distinct inputs, well, any given input gives a unique output. Emphasis on the word unique. Question? A circle would be a relation, not a function. Yeah. I'm coming to that. This graph definitely passes the vertical line test. No vertical line goes through it more than once. Another way to say that is all vertical lines go through it at most once. Your domain might not be all real numbers. And so in such situations, you could have vertical lines that go through the graph 0 times. Like, well, the upper half of that sideways parabola is still the graph of a function. There are vertical lines that don't go through it at all. What about the horizontal line test? That's when a function is 1-to-1. This passes the horizontal line test as well. No horizontal line goes through it more than once. There are some that go through it 0 times. This little curve here is not part of the graph. That's just an arrow pointing from the number 2 to that spot right there. It's 1-to-1. Any given output has a unique input. Such functions have what are called inverse functions. There are plenty of functions that are not 1-to-1 though, like just the plain old f of x equals x squared function. That's the graph of a function. It passes the vertical line test, but it fails the horizontal line test. There are horizontal lines that go through it more than once. Now, this is probably bringing up memories or maybe nightmares in your mind. And you say, oh, I remember that from 2 years ago, but before I said this stuff right now, you probably forgot it. And maybe you'll forget it by tomorrow. So you got to continue reviewing things to remember things. Question? Oh, okay. So you did a power function. Okay. Yeah, that's not an exponential function. Yep, you can make such functions that go through points like this, but it's technically not an exponential function. With exponential functions, we want the variable to be in the exponent. Okay. What about the alternative way to write this that I hinted that you could work on involving the number e? This is the simplest way to write the answer. But can it be solved using the special number e as well? Yes, it can be solved using the special number e. We could write our exponential function as f of x. Again, I'll go ahead and put a y in there. Y equals f of x equals a times not b to the x, but e to the, well, don't write a plain x because we need to give ourselves flexibility. E to the k times x. I tend to make my k's, when they're lowercase, cursive, because if I make them not cursive, they look like uppercase. I hope that's okay with you. That's a k. This is going to give us the necessary flexibility to go through the points that in question. We once again have the facts that 4 equals f of 1 and 16 equals f of 3. That's still the same information as before. Plug in the numbers. We don't have to write those dots if we don't want to, but you need to understand what these things mean if you don't write the dots. Once again, we can solve by division. Take the second equation and divide by the first equation. Once again, we get 16 over 4, which is 4, equals, take this divided by that. A e to the 3k divided by a e to the k. Once again, the a's cancel. Once again, you can subtract the exponents. 3k minus k is 2k. But solving that for k is harder. What do? We take the log of both sides. What are we doing when we take the log of both sides? We're really using the inverse function of e to the x, ln means in French, I'm going to botch up the French pronunciation because I took a quarter of French, but I cannot get the pronunciation right. This is like log natural, something like that. Sorry, people who speak French out there. Natural logarithm, written initially by somebody from France as log natural. Napier did that, maybe. Although I think Napier might have been British. Natural log base e of 4 equals natural log of e to the 2k. I am applying the natural log function to both sides. ln of x, natural log of x, log base e of x, is the inverse function of e to the x. And what that ends up meaning, we'll talk about this a lot more on Friday, is that over here, it's like the ln and the e cancel, and this simplifies to 2k. Is it really a cancellation? Kinda. It's not cancellation in the sense that you're used to, of one thing dividing by the same thing to give 1, or 5 minus 5 giving 0. It's not the exact same kind of cancellation, but it's a similar kind of idea, but with functions. Question again? E is a special number that's about 2.71828. On your calculator, you can find the number E, if you got a TI at least, right there. Can you see that? That little blue E right there. You can also find e to the x above the ln button. The two places I'm pointing there. If I do second E right there, there it is, 2.718281828. It looks like it's a repeating decimal, but that's just a coincidence. It's not a repeating decimal. The next decimal place is not a 1. It's something else. It's not a repeating decimal. That means it's an irrational number, kind of like pi. And it does play a very special role in math like pi does. It's especially useful in calculus. That's why we use it, is because it's so useful in calculus, as we will see why eventually. ln is log base e, and as far as what ln of 4 is, it's the power you've got to raise e to get 4. What is that? Type ln of 4, it's about 1.38629. If I take 2.71828 and raise it to that power, I should get 4, or really close. There's some rounding error going on there. If I do this, I get exactly 4. So ln of 4, about that, divide by 2, there's your k, approximately 0.693147186. Which is interesting, because that's actually the same as ln of 2. Isn't that wild? Well, it's not obvious, okay? We'll figure out why this works. ln of 6 divided by 3 is not the same as ln of 2, if that's what you're asking. So we'll talk about it more. Hang on. Probably we'll save that for maybe a little bit on Friday, or else next Wednesday. Next Monday's Labor Day. So what we have here is an alternative way of writing this function that's, you might say, more complicated, but there are certain ways in which this is better. And actually, because I'm using the decimal approximation, this is just an approximation. For the purposes of calculus, there are ways in which this is better, even though it's more complicated looking. This function, we should talk a little bit more about this function before we talk more generality, is exponential growth. And the fact that this base here is a 2, which is 1 plus 1, means that this function represents 100% growth for every unit that x increases. The fact that that second number is a 1, in general, it's going to be a 1 plus r that we'll write there. If that's whatever r is, in this case, it's a 1. If you convert that to a percentage, assuming r is positive, it represents that percent growth. So the fact that r is 1 means this is 100% growth. Every time x increases by 1 unit, the output doubles. So yeah, as x goes from 1 to 2, the output changes from 4 to 8. I didn't write a 2 comma 8 here, but 2 comma 8 is on the graph. F of 2 does equal 8. When x goes from 2 to 3, the output doubles from 8 to 16. When x goes from 3 to 4, the output doubles from 16 to 32. Doubling growth, that's the same as 100% growth for every unit that the independent variable increases by. Can that number be interpreted? It's called a continuous growth rate. It can be converted to a percent. It's 69.3%. You could use the word continuous growth rate. I will just do that here. It's harder to explain what that means, and I don't think I want to take the time to do that today. We'll do it on Friday. A 69.3% growth, continuous growth rate actually represents 100% growth for every unit that x increases. I know that's confusing. Why in the world is that the case? We'll talk about it more on Friday. To end class, our last 10 minutes here, let's talk some other generalities and some other notation. And maybe look at an application and talk about some things to expect on the assignment. Not necessarily the assignment due Friday, but maybe the next Wednesday. Our textbook for exponential growth writes this. Where A, this is going to be exponential growth. A is bigger than 1, K is bigger than 0. P0, they use P's here because they're thinking about applications regarding population. So P0 is like an initial population, but it doesn't have to be a population. They use a subscript here, P sub 0 or P naught. People sometimes say, don't say P naught. It's not N-O-T, it's P naught, N-A-U-G-H-T. Naught being essentially equivalent to 0. P naught. It's the initial population. When you plug in T equals 0 here, A to the 0 is 1. P naught times 1 is P naught. There's no function notation used here. Is that on purpose of maybe, I don't know. You certainly could use function notation. We could call this f of t. And yeah, we are using different letters for the variables, not x and y, but t and p. Don't let it bother you. It's okay. It's still the same idea. The p naught is kind of like my a. The a is kind of like my b that I used for my example. And using t and p here instead of x and y. It's okay. This is something you see all the time in science textbooks. You want to get used to it. Just not let it bother you. Focus on the idea. For exponential decay, like radioactive decay, for example, they actually use different letters for the, well, for the dependent variable. They use a q instead of a p. They still use an A, for the base of the function. Whoops. And let me just a second here. Yeah, that'll be a Q naught. Let me be consistent with the notation they use in the book here. They actually write negative KT here. A is between 0 and 1 in this case. K itself is positive, so negative K is negative. That's the way they write it. That's a common way to write it in science textbooks. I think that's the author's intent, is to relate this to science textbooks. So Q is the dependent variable here instead of P. Q naught is the initial value instead of P naught. Again, I think they're thinking about population applications here and quantity applications here, like quantity of a radioactive isotope that is decaying over time. That's what the authors have in mind when they write these kinds of things. And yes, again, you could use function notation in f of t or g of t or whatever you want here. It doesn't matter. It's still the same idea. And yes, A is between 0 and 1 here. If you write it in that form, you might use A equals 1/2 or 1/3 or 4/5 or 0.97, for example. The negative K is negative. K itself is positive, so negative K is negative. And when you have that kind of thing with base E, that represents exponential decay as well. The domain is still all real numbers, and the range is still all positive numbers, but now the function's decreasing instead of increasing. In both cases, with both exponential growth and exponential decay, the graphs are what is called concave up. What's concave up? I like to say it looks like a smile or part of a smile. The book says concave up means the graph bends upward, though you have to be careful when you think about this one. This is still concave up, even though the function's going down. It's bending upward as the graph goes down. A bit more precisely, concave up means the slope is increasing. As you move to the right, the slope gets bigger and bigger here, more and more positive. It's also getting bigger and bigger here, closer and closer to 0, though it stays negative all the time. Negative slopes over there, but they are getting closer to 0, which means they're increasing. I will re-say all these things. I don't just say things once. But you should spend time thinking about this as you do the reading. You should do the reading. The reading in this book's not too bad. It's fairly short readings, typically. 3 or 4 or 5 pages, typically. There's some calculus books that's like 10 pages each section. That does mean they have more examples quite often, but it's good reading. It's worth doing. Final thing we'll look at here is just an example application problem. I don't think I assigned anything for this first assignment like that, except actually for online people. Since your assignments are weekly, you'll get maybe problems like this. Here's a typical kind of exponential decay problem that you might see. It's about radioactive isotopes. Radium-226 in this case, okay? Radium, some element, 226 is maybe the number of neutrons, or I don't remember. Protons plus neutrons, something like that. It's radioactive. It changes to some other form of radium or some other element over time. It's got a half-life of 1,620 years. That means whatever amount you start with, and I just imagine it's sitting there in some pile, like some dog doo-doo or something. Okay, no, sorry. And it's decaying over time. The amount of it is getting smaller and smaller. Okay, that's misleading. It doesn't mean it's actually shrinking. Yeah. Yeah, the amount of this radium isotope is what's decreasing. There are, the mass might be getting smaller because like neutrons or whatever might be shooting off and going into outer space or something. But anyway, this is the function representing the amount of radium, quantity of radium as a function of time. Q0 is not specified. This says, why is that the case? And they also ask you to figure out what percentage of the original radium is left after 500 years. To do the second one, you just plug in T equals 500. And maybe you, okay, let's go ahead and do that second part real quick. 0.999572 to the 500th power is about 0.81. What that means is after 500 years, about 81% of the original amount is still there. That's what that means. For part A, as far as the Y goes, I think there's a brief explanation of this in the book. There's another way to write exponential functions when you're thinking about half-life applications. Let me use f of t here. That's convenient. If you're thinking about half-life, you can write an exponential decay function as Q0, Q naught, times 1/2 to the T over whatever the half-life is. In this case, it's 1620. I guess I'm doing this problem for you. That's the same as Q naught times 1/2 to the 1 over 1620 power to the T power. That's a property of exponents. And I claim that if I do this thing in my calculator, 0.5 to the 1 over 1620 power, I didn't make a mistake, I should get 0.999, whatever it was. 0.999572. Yeah, there it is. This is a convenient way to write half-life functions or exponential decay functions when you know the half-life. You put a 1/2 there and you put T over whatever the half-life is there. And by doing this, you can get the form that's written in the book. Which represents a very small percent decrease per year, less than 1%. I'll let you think about it. You can figure out what percent the amount decreases per year. It decreases by 50% over 1620 years. That's the meaning of half-life. Okay. All right. We're at the end here today.